So welcome you all. In the last lecture, uh, as far as the module number 3 is concerned, we talk about the network functions, its properties of the driving point impedance properties, the properties of the network functions. At the same time, the four different categories, namely impedance function, admittance function, current transfer ratio, voltage transfer ratio, and its role in designing and analyzing a stable or fruitful network in terms of transfer function or in terms of the impedance function, okay, and their applications. Now, in continuations to in the lecture series of module number 3, today we are going to initiate a new topic, that is the one of the basic fundamental topic, that is the analysis of three-phase circuits. Okay, so as you all aware, as a electrical science domain, that is whether you are a student of electrical and electronics engineering, that is the triple E branch, or the sister concerned branches the electrical engineering, or possibly electronics and telecommunication engineering, or the instrumentation engineering. So we know that fundamentally that we have two options available. The basic option is that the single phase supply, and the second option, which is more standardized, that is the three phase supply. So if you say your day-to-day life applications, you can come across with the different applications. You can come across with the different applications where uh, you can invariably uh, in touch with single phase supply based equipments, and you also have experienced the advantage of three phase supplies. Now when you switch from the single phase to multi phase, and here for me multi phase meant to say n is equal to 3, so that is the we restrict to three phase. So one should be noted that as you are jumping towards the higher degree of phases, like for example, when you switch from the single phase supply to the three phase supply, so you know that the other than the ground terminal, okay, to establish the uh, remember the neutral and ground are different, okay. So to establish the contact with the ground terminal, you have three different phases, unlike the single phase supply. So obviously the uh, number of, or you can say that the amount of conducting path you required is also increased by that many times, okay, as the phase is, okay. So obviously if it is a two phase, so you required two pair of conducting surface, and if you require a three phase, so it required a three phase of the conducting surface. So now the question comes that why not six phase or nine phase? Isn't it possible that we can attend the higher phase supply? Certainly yes. The answer is yes. But as you know that again the number of conducting surface will be equally increased, and it will also add the additional amount of burden cost in terms of the operation cost, and most importantly the maintenance cost as well. And at the end of the day, remember, it doesn't matter what technology you are going to enjoy, but at the end of the day, as an end user, ultimately you have to bear the entire cost. Okay, your utility or the power generation company is not going to bear ultimately that cost. Okay, they are going to transfer that cost to you at the end of the day. Okay, it's just like a very simple uh, analogy that tomorrow if there is a product, okay, so electricity is nothing but it is a product. So a company, there is a company who generate it, there is a company who transmit it for the long distance, that is called your transmission companies, and then there are the utilities, okay, or the companies that is take care of the responsibility to supply the electrical power to the door to door net, okay, because that door to door is actually end user, we are the end users, right? So remember that whatever technological operation is going on, okay, at the end of the entire development cost, operation cost, the all the feasibility cost is at the end of the day going to be bear by the consumers, right? Now, so therefore there is a it's a matter of research. A lot of people are actively involved in this area, but it was quite established. decades back that the three phase is going to be a in general acceptable if you get the advantage to intact the advantage of the multi-phase network supply system. Okay, so yeah, as you can seen that the most important advantage of the increasing phase supply is that you can draw more and more power. Okay, so if you can draw more and more power, so that means with the same kilometer of distance you can nullify the losses. Okay, remember the per unit per kilometer distance if there is a conducting path, it include, okay, it imposes some resistance. So remember in that case the amount of resistance loss, because the power dissipation loss will be the remain same. Okay, but if you are going to interact with the power phase supply in the mathematics, you can see that you can increase, you can enhance the power capacity. Okay, the instantaneous power capacity. Okay, okay, and that is almost the root over three times. So that is the advantage of your three-phase network. Okay. On the contrary to that, obviously, little bit of burden we are bearing in terms of the cost of expenditure. Right? Okay. So let us proceed with this under the head of this lecture series. So we are first going to see brush up the some fundamental aspects. What I believe that mostly you have to come through. But remember, when we talk about the fundamental aspects here, we are going to restrict the our approach to the instantaneous power only. Okay, that is the power analysis part, and then we are going to very quickly jump to our actual agenda as per the syllabus. So if you can see that what about the pure power in a pure resistive circuit? So let us go one by one. That there is a source and there is a resistive uh, network. Okay, so the entire resistive network, for the simplicity, here we have imposed, we have equivalent circuit is represented as the R. Okay, so R is the resistance of that entire network, and V of T is the supplying of the voltage source, and I of T is the response, that is the instantaneous current. So you can very well appreciate that the average power in this particular case is equal to the constant. Okay, so the maximum value of V and the maximum value of I, that is the Vm Im, or in a simpler word, as in can see that in this particular side we have designated as capital V into capital I. Okay, remember small I of t is the instantaneous value, capital I is the actually it's a maximum value. Okay, the highest magnitude of the current or voltages, right? So as you can appreciate that in this particular case, that the amount of power you are retaining, okay, that is the calculative, and it is a non-zero value as far as the resistive power is concerned. But remember, it is the same element which actually causes the loss, that is called your dissipation loss or power dissipation. Okay, in other words, fine, or that is which is proportionally equal to I square R loss. Fine, yes. And why do we need it? Because there is some provision which is used to restrict the flow of current. It is simply like that, when you are driving a car, you require a braking mechanism. If not, then probably you will be able to reach your destination. Okay, but probably you cannot enjoy your destination. I hope you can understand. So braking mechanism is very important, though it is a resistance, but it's a very important in our real life scenario. So equally important in case of the physical applications such as like electrical energy generation, supply, and the distribution and the supply. Okay, so that is so pure power in the pure inductive circuit, unlike the resistive circuit. In case of the reactive circuit, as you can appreciate, okay, through the mathematics, that if it is an inductive circuit, so please be noted, how do you know that it is an inductive circuit or capacitive circuit? Because both are the reactive component. Fine. So you can see, you can appreciate that if if you look at the instantaneous response of the current and the instantaneous response of the voltage, normally the instantaneous response of the current is lagging, okay, by the 90-degree as compared to the phase angle of the voltage. Okay, so say for example, if you say that your uh, voltage phase angle is 0 degree, then the current phase angle will be minus 90 degree. If voltage phase angle is at any moment is 90 degree, then the current phase angle at that moment of time will be equal to 0 degree. So the current response or the current instantaneous characteristic of the current is lagging by, you can say that, 90 degree as compared to the voltage characteristic. Okay, so that is the indication of a pure inductive circuit. If you appreciate that the response of the voltage or current, okay, in terms of the instantaneous power is operating at the twice of the central frequency or twice of the operating frequency or rise of the resonant frequency. You can say that your supply frequency is operating at 50 hertz. Okay, so in that case, it is going to be operating at in general, you can say at 100 hertz. Okay, so that is the point what I wanted to convey. But if you look at the average power, what is the average power? Obviously that is the zero. Okay, because the amount of power is drawn, okay, by the inductive circuit from the source in the positive half of the cycle, so that actually it is used to store in the form of magnetic field. Okay, and the same amount of energy is discharged, okay, by the inductive element, okay, to the source. Okay, it is reverting back. Okay, it is giving back to the source, okay, in the next half of the cycle. So if you see, the average of the power cycle becomes zero. Similarly, if you can appreciate that the power in the capacitive circuit, what will happen? The behavior of capacitive and inductive circuit is exactly the reverse. It is 180-degree phase reversal, you can say. So obviously, again, if the voltage phase angle is 0 degree, then in this case, what happened? The current will is going to lead rather than lag by the 90 degree. So if voltage angle is the 90 degree, then the current at that point of time will be 180 degree. Okay, I hope that's very easily clear to you. But as far as, obviously, and that is the reason that as far as the instantaneous equation of the power response is concerned, okay, when you will observe through a inductive circuit and as compared to the capacitive circuit, in case of capacitive circuit, you see that you are getting a negative response. So this negative value is actually nothing but it is an indication of the 180-degree phase reversal, nothing else. But as far as the average power is concerned, that response will remain same as like in case of the inductive circuit. Okay, the difference is that here it is going to mount in terms of the electric field rather than the magnetic field. So in each quarter, the amount of energy it is used to charge the capacitive network is going to revert back to the voltage source in the next quarter of the cycle. The same thing is happening in the positive and negative half of the cycle, and therefore the average response of the circuit in terms of power is actually zero. So it's basics one. Fine. Now, as far as the AC circuit is concerned, you know that there is a complex power, okay, and which is actually a cumulative complex conjugate response of the real and the reactive power. So, therefore, as far as any AC circuit is concerned, typically to satisfy the 100% requirement of the product of voltage and current, that is the power, we generally call it the apparent power, unlike the, okay, DC circuit, unlike the DC circuit. Remember, so here your response is varied. So that means the complex power unit will be the volt ampere. Okay, yeah. Okay, now this volt ampere, okay, complex power, the apparent power rather, I would say, has actually two factors. That is the real power and the reactive power. So if you talk about real power, so let's say assume that the phase angle, okay, from the response is equal to phi, okay, or psi you can say. So that is equal to vi cos phi. Fine. So that is the wattage. That is the actually amount of energy what you are using as a consumer, what you are consuming. Okay. If you look at your electrical circuit in your day-to-day life at your home, at your hostels, or in your offices, or in the industry, okay, primarily maximum time we are the basically a resistive network. So that resistive network is consuming the power in terms of wattage. Okay. Whereas if there is a exception, what can be the possible exception? Okay, so for example, you assume that the induction motors, okay, you assume there is the inductive circuits. So if whenever the induction motors are normally used, in which case in the industries, okay, it's highly used, okay, popular as far as the manufacturing sector, food, beverages, chemical sectors, okay, um, steel melting plants, steel plants, okay, or the aluminum industries, heavy electrical engineering. Okay, in these cases, you can see that they use the induction motors of their distinct advantage. Okay, and now, other than that, in today's scenario, when we are completely surrounded with the hundreds of the thousands of electronic gadgets all across the world, okay, so in that case, these electronic gadgets are normally discharging the uh, you can say in one way it is nothing but it is a noise or it is a dust to the electrical system, okay, in terms of the reactive power. Okay, so they are injecting back the reactive whenever you are going to charge a laptop or whenever you are going to charge a mobile phone. Okay, it is going to inject, okay, a prominent amount of reactive power back to the grid. So it is nothing but, in other words, it is going to actually pollute your quality of the power. Okay, because your real quality, the 100% pure power is the real power, and to achieve that you have to make your power factor is equal to 1. Okay, that is something is the idealistic one. Again, we should not achieve it. Okay, we should not think about it at all. Why? The reason is that when you talk about the kind of prime movers, okay, see, remember nowadays the a lot we talk about the renewable energy and the participation of renewable energy, okay, in your total amount of energy consumption graph is increasing rapidly, okay, to intact or to tap the greenhouse gas emissions, okay, or to tap the carbon footprint. That is the advantage. But the disadvantage is that most of these modern sources, unlike the conventional power generation plant, thermal power plants, gasified power plants, IGCC power plants, hydropower plants, nuclear power plants, unlike the conventional sources of energy, you do not have any prime movers other than the wind. Okay, wind have a certain kind of prime mover, but obviously you know that the prominent amount of wind energy as an energy source is not available all across the world, because minimally the technology suggests, today's technology suggests that you have minimally required at least 6 meter per second to 8 meter per second of the wind flow continuously to tap that particular wind energy in form of the electrical energy. Otherwise it's a waste. Okay, so therefore, if you look other than the wind, if you look at the solar energy, biogas, fuel cells, tidal energy, so there are so many energy sources, but most of sources are basically the static. Okay, it's not, there is no dynamics are involved into it. There is no prime mover component is involved. Then how will you take to control the reactive power? So then it moves to the different age of technology, and if you have an interest in the renewable energy, you can do lot of research in that area, and in fact it is a now very prominent research area. Okay, you can think about the use of supercapacitor, you can think of the use of the basically the energy storing devices. Okay, supercapacitor as a storing devices, okay, fuel cell as a storing devices, there is a different mechanisms, things are going on. So either there is a one option, but the thing, the fundamental aspect is that you cannot make the q, that is the reactive component vi sin phi is equal to 0. You have to have something, right? And which is gives you certain amount of var, and that is the amount which you are compromising from the wattage. Okay, and that wattage plus the reactive power, that is var, volt, okay, volt ampere reactive, in total it gives you volt ampere. Remember this. Okay, so typically we operate at the power factor of depending on the type of power generation sources, we vary from around 0.55 to 0.8 in general. Okay, yes, with the modern tools, modern technology, we are able to achieve even around 0.9 also sometimes. Okay, that we have really tested in our university environment, in our real life environment. Okay, couple of times. Okay, through the appropriate by using the appropriate electrical gadgets. Okay, as far as the supplying of the power in the different sectors of our university, whether it is a hostels, whether it is a residential area is concerned. Okay, so the good news is that still we are now able to intact or achieve around 0.9 factor, okay, at the distribution level, but definitely you cannot make it one. Okay, not advisable. If you look at the in the proceedings of the slide, here as you can see that S is equal to P plus JQ. So that gives you nothing but it is a complex power in terms of voltage phasor and the current phasor. Fine. So I hope that you will be able to appreciate this. And the next time you are measuring, remember as far as the residential or applications or office like applications are concerned, okay, your utility gives a unit. Okay, they charge you in terms of the consumption of energy in terms of unit. And can you name that what is the unit? So basically a kilowatt. Okay, so the 1 kilowatt is nothing but it is a one unit. Okay, for a very big size of consumers, okay, they generally gives the demarcation in megawatts, but in that case still remember the standardization is same, that 1 unit is basically ultimately converts to the 1,000 units. So 1 unit of electricity consumption is nothing but it is actually consumption of the 1 kilowatt of energy by you. Next time you remember it. Okay, yes. So if you look at the complex power consumption, so leading to Ohm's law, so here what you are going to follow V is equal to Z into I in place of Rf into S, because we are dealing with the complex power. So the average amount of power, the mod of I square R you will get is equal to maximum value of current, that is Im square by R 2 into R of wattage, whereas the as far as the complex power is concerned, that is mod of V square by Z or mod of I square into Z. Okay. So if you look at the power angle and the power factor aspects, So in that case, you can say that your sine phi is nothing but is the ratio of reactive power upon apparent power, whereas cos phi, that is you are coming from the real power factor side, that is the real power upon the apparent power. Okay, so this you can say that phi is going to deal with the power factor angle. Okay, and it has you can say it produces the phase relationship, okay, between the applied sinusoidal voltage and the circuit current. So circuit current, as you can see in this demonstration, we have been considered as I, and source is supplied as a V. So and in that case, there are a certain number of sum of the powers. We are assuming that there is a distribution of power. So I ask you a basic, very fundamental question, that if you look at the entire distribution of the supply, okay, that is from a local transformer, a certain number of units, certain number of energy meters are actually energized, and through that energy meters you are getting a power, and then that energy meter is dedicated to supply the power or connect yourself to the local grid, or you can say that to local transformer, the local grid, and distribute, provide the availability of supply, or in other words the energy to each and every power consumption devices at your home or offices. Okay, so these components or the energy consuming devices are connected in series or parallel. That is the question. Think about it. Okay, it's a very basic thing. I think you could have been take idea, okay, from this demonstration as far as figure number 7.13 is concerned. Okay, so if you see the as shown in this particular figure, it's a very interesting characteristic and very important characteristic also. Okay, what shows the variations of the apparent power and the line losses, okay, with respect to the power factor. Okay, so in y-axis you have a graph of the apparent power which is varying with the power factor, and you also have a graph of the line losses, okay, which is responsible to carry that particular power from the generator to the consumer and user with respect to the power factor. You will appreciate, you can see in this particular graph, when the power factor is equal to exactly 1, so that means there is only and only the real power. That means the entire power is available in terms of the wattage. In that particular case, you see there is not a zero, but the amount of apparent power, and if you see the characteristic of the line loss, both are merged at that particular point when the power factor is exactly 1. So what it shows that in that case the amount of line loss is minimal. Okay, why the line loss occur? Because the current is actually drives or flows through that conducting surface. Okay, and while it is flowing or basically driving through that particular conducting surface, it experiences the reluctance, it experiences the resistance of that particular conducting surface, so which increase the basically loss. Okay, so remember this transfer of loss is also added into the account of your bill. So more than line loss is, okay, to consume the same amount of power, higher the bill you will get. Okay. So remember that the quality of the conductive surface is also good for your reduced bill, and at the same time, the higher the power factor you can attend is also good for your energy bill, because then you will get the lesser energy bill. Okay, you know the reason is what? Basically, if you see the apparent power, what is that? The product of V into I. So ultimately, the current is driving that line current you are driving. So when the power factor is reducing, as you can see, then to meet that amount of power demand, okay, basically you have to draw the more powers. Okay, so when you draw more power, basically you are drawing more V into I. So in as good as actually the increasing the participation of the line current is also increasing. So if the value of I is increasing, so you know that the power dissipation loss is proportional to I square. It's I square R. Okay. So it is the loss is increasing the exponential times. So that's why, as you can appreciate, the value of Vi is increases it following a non-linear path. It's a parabolic path. So in that case, the line loss is following a cubical path. Okay. So it is exponentially increasing, right? So that's why the power factor should be as higher as possible, close to the one, if not exactly one. That is the significance of the power factor. I hope that this fundamental aspect is now very well clear to you. So to continue our discussions, the as far as the significance of power is concerned, the couple of mathematics are in front of you. So you would appreciate that you can see that the power triangle relationship, okay, in terms of the VAR and which also leads the required amount of capacitance. Okay, how you can use the capacitance to increase, or you can say that primarily improve the power factor, okay, by using the relationship as mentioned in your 7.40. Okay, so that is the way that how the capacitance can be used as far as the RMS voltage are concerned, okay, to supply the required amount of reactive power. Okay, so from the parallel triangle, and then that way you can improve the power factors. Okay, so here is a problem is assigned for you, that a standard equation is given, source equation is given, phi and omega is given 314 radian per second, phi is equal to 10 degree, right? So with the help of this particular magnitude or instantaneous value of the source voltage and the source current, okay, the supply current through the conducting surface, it is a two terminal network is mentioned, and you are asked to calculate some uh, basic things like the real power, reactive power, frequency of the reactive power. Okay, is the real power being supplied to the two terminal network? That the question is asked to you. Remember, the party is very exclusive. Okay, draw the power triangle. State whether the power factor is lagging or leading. So that basically decides that whether your surface is actually inductive in nature, or there is more inductance, involvement of inductance or the capacitance. Right? Okay. So, and similarly, is the network supplying reactive power to the source? Okay, whether the network is supplying reactive power back to the source or not. Okay, what is the reactive power factor? Okay, so these things probably you can calculate. Probably you can take 5 minutes of time and solve it, and then we will also move ahead for the couple of new questions to brush up our fundamentals. Okay, followed by the next topic. So I hope that you are able to solve the problem. Take one more problem. Okay, that's a very another fundamental one. Okay, I would again insist you that you take your couple of minutes of time and solve this problem as well. We have a couple of around 2 3 problems. Okay, I would suggest that you solve each and every problem here itself. Okay, again for the given circuit, that is a basically parallel RC circuit is given, and your job is to calculate the real power, reactive power, apparent power, power factors. Okay, for this particular given problem, followed by the real power, reactive power, apparent and power factor angle across the parallel terminal AB. Okay, and what is the magnitude and nature of the power contributions by the capacitors? Draw the power angle, and obviously the supply frequency is given 300 hertz. RMS voltage is 25 volt of the source, so you can say 25 plus J0 you can write, and solve this. So let us go ahead for the next problem. Okay, very interesting one. So this is, you can say that is nothing but is the simplified model of the source, power generation, power transmission and the distribution, and at the end of the day load, that the Thevenin impedance, the circuit impedance, the load impedance, and the Thevenin voltage, you can say. Okay, so it's a simplified model of irrespective of any degree of complex networks, right? So 440 volt RMS generator supplies a load to a load that is 15 plus J20 omega, and through a transmission line impedance that is 1.5 plus J4. So remember that if you look at the Thevenin impedance of the transmission line, circuit impedance is relatively less, far less as compared to the load impedance. The point to be noted. Okay. Okay. And then calculate the line current, load voltage, real and reactive loads, apparent power supplied to the generator, power factor and power factor angle of the generator, what impedance Z should be connected in parallel across the load, okay, ZL, to ensure the maximum power transfer takes place. Remember, that should satisfy the complex conjugate pairs, right? And other than that, that means ZTL should be the complex conjugate of ZL. So from there you can get your answer. What is the power factor of the generator under the condition of the maximum power transfer? When the power transfer, maximum power transfer you have achieved, what is the value of the power factor? Okay, obviously I hope that you got the answer. What is the maximum power transfer? Obviously that things you have to calculate. Very interesting problem. I think you solved it. So in continuation the problem, here are the, for your information as far as the last problem is concerned. Yes. Standard and intermediate steps are already given, so you can verify the solutions. Okay. So let us switch to some couple of more problems. Another balanced three-phase 400 volt uh, delta connected load network is given. Okay, so from here, okay, so typically you believe that in a very generic fashion, in a standard fashion, the supply side is typically connected in terms of star manner, and the load side is connected typically in the delta manner. Okay, delta connected network. So there is a very specific reason behind it. Mathematically you can have any combination, but practically that is the most preferred option. The supply side is the okay, so you have a star and delta. Load side is also star and delta. Investigate about it. I would say that what combination should be the best as far as the interconnection of the three-phase network is concerned, from the three-phase source to three-phase load. Okay, and along with that, you try to solve this particular problem. Sorry. Okay, another couple of very interesting problem, with which we are going to move ahead our discussion toward three-phase side. Okay, three-phase 50 hertz 400 volt system feeds a load of 25 kilowatt with a power factor 0.7 lagging. Remember, so it's an inductive one. Okay, and as shown in figure, three capacitance are connected between the lines across the load. Okay, lines across the load to improve the power factor to 0.85. So remember, power factor is lagging to 0.7. So to improve the power factor, you have connected the three uh, capacitors. Okay, connected between the lines. So involvement capacitors, what it will do? It will reverse the analogy of the phase as compared to the inductive to 180 phase. So therefore, you are able to improve the power factor. Okay, another fundamental aspect. Remember it. Okay, so whenever you want to improve the power factor, what you need to do? Okay, determine the resultant current drawn from the supply and the value of the capacitors. Okay, so what I did. So here are the, you can say that this is just for your reference, the reference for the three-phase star connected sources. So as you can know that if it is three-phase star connected, as I show, as I have shown in my circuit diagram, we have taken a three sources VA, VB, VC through the phases, and with respect to neutral, so it is you can say that VAP is nothing but VA minus VB, VBC minus nothing but VB minus VC, and VCA is nothing but VC minus VA. Okay, or VA minus VC you can take. Okay, with respect to the line current. So from here, as far as the three-phase star connected supply voltage is concerned, here you can see that basically the line voltage has some interrelationship with the supply voltage, but whereas you can appreciate here that as far as this line current is concerned, say IA, it is the same current which is passing through this VA with respect to the neutral. So the line current and the phase current is exactly same as far as the three-phase star connection is concerned or Y connection is concerned. So therefore, in three-phase delta connection, okay, or in pi connection, what will happen? The line voltage will be equal to the supply voltage. Remember, okay, and the in case of the star connection, the line voltage is root over 3 times of the phase voltage. In case of delta connection, line current will be root over 3 times of the phase current, as it is the complementing each other. So the generation of three-phase voltage, here you can see that that frequency can be correlated with the speed of the prime movers, and the number of poles. P is the indication number of poles upon 120 is the cycles per second or hertz. From there you can get. Okay. So if you want to retain the, say for example 60 hertz or the 50 hertz, then what you should, the what numeric combination you should choose to get the 50 hertz. Understood? Then the value of VA, VB, VC, they all are to the rest two are aparted with the 120-degree phase reversal. Okay, so say if VA is operating at 0 degree, zero phase angle, so in that case VB is operating at minus 120 degree and VC is operating at plus 120 degree, you can say, or minus 240 degree. Clear? So I guess that you would be able to appreciate it. And this is another last practice problem I have given you. I would insist you that you also solve some couple of minutes for its understanding. And then with this, we will conclude this discussion. So if you see this interesting phase of a problem, that three-phase star connected balance voltage source. So this balance terminology has come, which we are going to discuss in the next aspect. It's very important, balanced and unbalanced. Okay, uh, load aspect. So balance source with the line voltage of 230 volt is supplying to a star connected balance load of that is the complex load. So ZL is equal to 5 plus j 3 omega as shown in the figure. So you say that the star and sorry, the source and the load both are connected in the star fashion, as I've been told you to investigate just few slides back. What is the best possible combination if you have a flexibility to do so? Okay, so if the source impedance ZS is equal to the magnitude is given, and the impedance of the each line ZL, okay, is also given, that the calculate in each phase the load current, load voltage, what is the current in the neutral conductor, draw the phasor diagram showing that the current and voltage in phase A and the three phase current and voltages at the load terminal. How will the load current and voltages change the line impedance if at 0? If the line impedance would have to make 0, then what kind of changes you would require to incorporate in line voltage and line current? Very, very interesting problem. I suggest that you should solve it, and obviously this will help you to brush up the basic fundamental things of the three-phase analysis. Okay. So with this, we are going to proceed in the next slide, which is the major agenda of our topic as far as the balance and unbalance aspect of the three-phase power is concerned. Okay. Thank you.